Good morning everyone. I am Lavanya R from 4th Sem AIDS and my topic is biocomputing using DNA structures. What is biocomputing? Biocomputing is an interdisciplinary field that uses biological systems and molecules to perform computational tasks. Here, biocomputing uses biological materials like DNA for its computation. It leverages the information storing capabilities of DNA for complex problem solving. Why DNA is used in computing? High density. 1 gram of DNA can store 215 petabytes of data, so DNA is used in computing. Stability and energy efficiency compared to silicon chips. Key milestones in DNA computing. In 1994, Leonard Adleman solves the Hamiltonian path problem solving using DNA. Growth in DNA-based logic gates and molecular algorithms. Basics of DNA structure. Double helix structure. DNA is made up of two strands forming a helical shape. Nucleotides A, T, C, G. A is adenine, T is thymine, C is cytosine and G is guanine. A pairs with T with 2 hydrogen bonds. C pairs with G with 3 hydrogen bonds. How DNA performs computation. DNA computing is based on natural properties of DNA strands. First one is hybridization. Complementary DNA strands naturally bind together. This pairing can represent logical decisions like AND, OR and NOT operation. Second one is strand displacement. New DNA strands can displace existing ones if they have a better match, enabling logical processing. Third one is self-assembly. DNA strands can automatically align and form structure based on their sequence. Example, solving the Hamiltonian path problem. The first major demonstration of DNA computing was in 1994 by Leonard Adleman. He used DNA to solve the Hamiltonian path problem, that is finding a path through a graph that visits each node exactly once. Steps included in that. First one is encode each city and path as DNA sequence. Second one is mix DNA in a test tube. Complementary strands automatically bind, representing all possible paths. Third one is filter out the incorrect paths, leaving only valid solutions. DNA has logic gates. Similar to traditional computing, DNA strands can represent logic gates: AND gate, OR gate and NOT gate. AND gate is used only if both input strands are present. The reaction completes. OR gate, if either input strand is present, the reaction completes. In NOT gate, the absence of a strand triggers a reaction. Advantages of DNA computing. Parallelism. Billions of operations can occur simultaneously in a single test tube. Data density. 1 gram of DNA can store 215 petabytes of data. Low energy consumption. DNA reactions are energy efficient compared to electronic circuits. Limitation and challenges. Error rates. DNA reactions are not always perfect. Errors can occur. Scalability. Large computations requires precise biological control, which is complex. Speed of read and write. Current methods of reading and writing DNA data are slower than electronic systems. Future implications. Integration with quantum computing for enhanced speed and data processing. Use in biological diagnostics for real-time disease detection. Massive data storage solutions for global data needs. Conclusion. DNA structures allows for unique computational possibilities. Future technology may harness DNA for medical, storage and processing advancements. Why DNA computing is important? It promises breakthroughs in data handling and biological problem solving. Thank you.